Hi, welcome to the next video for first topic in Year 11 Chemistry, Materials and their Atoms. This is subtopic 1.4, which is looking at the periodic table. And this periodic table looks a little bit different, I guess, from what you would have seen before. But this is a periodic table which is now showing the relative abundance of atoms in the Earth. So you can see things here like silicon, which has a very large area here, that has a relatively high abundance, and then you start to get through and you got things that are starting to decrease in abundance. Little things here with this little icon here, these are all things that are used in mobile phones. Okay, so just a bit of a different way of looking at the periodic table there, looking at it by abundance rather than just it normally set out in the rows and columns that we're used to. So when we're looking at a normal periodic table, not that weird one I showed you at the beginning, we organise it into groups. These are the columns, so they're the bits that go up and down. Okay, and then we have periods, which are the rows that go across. Okay, so groups up and down, periods that go across. Each group or column has the same number of electrons in the last shell. We call that last shell the valence shell or outer shell. All right. So everything in group 1 here has 1 electron. That has 2 electrons, 3, 4, 5, 6, 7, and 8 as we go across. Okay. Each period or row has the same number of electron shells. So everything here in period 3 has 3 electron shells in them. We'll go into a bit more depth there. If you want a really good overview of this, this is another video I've put together. You can have a look for that. That's giving a whole overview of the periodic table and goes through each of the different trends I'm about to look at now. So the first trend we're going to look at on the periodic table is what's called metallic nature. So the periodic table is actually split up into things called metals and non-metals, and then we've got metalloids. So metalloids, and there's only 6 of them over here. You can see these yellow ones. So boron, silicon, germanium, arsenic, antimony, and tellurium here. Okay, these ones are metalloids. So they have the properties of both metals and non-metals. Okay, but then we've got metals over here, and then we've got non-metals over here. So we'll look at the properties of those a bit later in a different video. So metals like to lose electrons though when they react with other atoms. Okay, so all of these metal atoms here, they want to give out those valence shells electrons so that they become stable. Right? A stable atom is one that we generally say has a full outer shell. So these ones here, helium, neon, argon, krypton, xenon, and radon, these elements through here, they're called the noble gases. Right? They're all stable because they already have 8 electrons in their outer shell, apart from helium, which has 2 in its outer shell, but they've all got full outer shells. Okay. If an atom likes to gain electrons, it's classified as a non-metals. All these blue ones over here, all right, so from carbon all the way down to radon and iodine, all of these ones here, they are non-metals. They like to gain electrons. So we normally have metals giving up electrons, non-metals gaining electrons, and that's how they form bonds. The trend for the periodic table is that metallic nature decreases across a period. So as you go from left to right, we decrease in metallic nature. And as you go down the periodic table, metallic nature increases. So francium over here, this is the one that really wants to give off electrons the most. So francium is the most metallic metal. Okay, so this metallic nature increases down a group and decreases across a period. Atomic radius is defined as the distance between the center of the nucleus and the outer shell, that valence shell. Okay, so it's just the distance here. There's a couple of things that impact that distance. First one is obviously the number of electron shells. Okay, the second one is also the number of protons in the nucleus here. So the stronger the attraction that the nucleus can put on the electrons in this outer shell, the smaller the atomic radius. So it kind of just starts off here, and the more attraction the nucleus can put on, the smaller the actual atom itself gets as those electrons are pulled in towards the nucleus. So the trend on the periodic table is that as you go across a period, the atomic radius decreases. Now you've got to remember that for a period, they all have the same number of electron shells. So everything here, period 3, sodium as we go across, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, they all have the same number of electron shells. So what that means is that all of these with 3 shells, the only thing that changes is there's more protons in the nucleus. So chlorine here has 17 protons in the nucleus, sodium has 11. So more protons in the nucleus can pull those electrons in closer, so chlorine has a smaller atomic radius. That's why it decreases across a period. As you go down a group, atomic radius increases, and that should make sense because every time you go down, you're going from 1 electron to 2 electron shells to 3 electron shells, 4, all the way down to francium. Okay, so you now by this stage got 7 electron shells, so it's much bigger than if you only had 2 electron shells. So atomic radius increases down a group, decreases across a period. Electronegativity is something that we say is the ability of an atom to attract electron density to itself in a bond. So this will make a lot more sense when we go to into the next topic when we're looking at polarity in bonds and we look at what happens particularly with covalent bonds. It's the ability of an atom to attract electrons to itself in a bond. So this comes down to basically how easily can that nucleus in the middle pull electrons in those outer shells, okay? So if there are more protons in the nucleus, it can obviously attract electrons more strongly. However, as you increase the number of electron shells, the nucleus finds it harder to attract the outer electrons, so electronegativity decreases. Not surprisingly, metals, they want to give up electrons, give them away, so they're not going to want to attract them to themselves. So metals have lower electronegativity. So as you go across the period in a periodic table, all right, the electronegativity increases. So everything goes towards F over here. Fluorine is the most electronegative element. Okay, that's the one that will attract electrons most strongly to itself in a bond. Francium over here at the other end has lots of electron shells, so the electrons are really far away from the nucleus and it really doesn't want to attract them, it wants to give them away. So francium has the lowest electronegativity. So electronegativity increases across a period, decreases down a group. Valency is called basically the charge that an atom gets when it becomes an ion. Okay, so you can use the periodic table to understand what the general charge of an atom will be, and this relates to their valence electrons, the electrons they have in their outer shell. So everything here in group 1 has 1 electron in its outer shell. We know that metals want to donate electrons or give them away. So all these atoms in group 1 are going to give away 1 electron. Now, an electron has a negative charge. So when you get rid of 1 electron, 1 negative charge, you end up with 1 positive charge left over. So if you had 7 protons and 7 electrons to start with, I'll do it with fingers, it's easier so you can see. So if we have 4 electrons and 4 protons, let me start that again, sorry. If you have 4 electrons and 4 protons, okay, if you take away one of the electrons here, you still got your 4 protons, which are positive, but now you've only got 3 electrons. So overall, you've got a 1 extra positive charge on this side. So everything in this group here has a 1 plus charge. When you get to group 2, they have 2 plus charge. Transition metals are a little bit different. Transition metals, what you can generally assume is they're normally got about a 2 plus. They can be 1 plus or 3 plus. Some can be 4 plus. Actually, no, not transition metals, sorry. But they're normally 2 plus. So if you go with a +2 charge for the valency of an ion of a transition metal, that's an easy thing to do. Then you go to +3 and +4. Now this group here, group 4, has 4 electrons in its outer shell. So it could either attract 4 electrons or it could lose 4 electrons. Generally what they do is they lose 4 electrons to form a 4 plus charge. But once you get over here to nitrogen, this group 5, they only need 3 electrons to get their full outer shell of 8. So now what that means is that these will want to pick up 3 electrons. So now these become -3 for their valency. -2, -1, 0. So this can be useful if you're trying to write the formula for a chemical. So if you've got something like magnesium phosphate, you can put magnesium, you know that's in group 2, so it's going to be 2 plus. Phosphorus, shouldn't be magnesium phosphate, sorry, magnesium phosphide. Here, phosphorus has a -3, so you can combine them together. So it can be useful to actually use the periodic table and their valencies as well. All right, so that's a brief overview of the periodic table. There is another video I said at the start of this one that you can have a look at as well, but you just need to remember those trends going across a period and down a group, and hopefully this has been pretty straightforward. Thanks.